Okay, this video is going to look at this function and find first and second derivatives so that we can locate where the function is increasing, decreasing, where the local maximum and minimum are, and where the curve is concave up or concave down. And if it changes, where's the point of inflection? There's going to be a lot of calculations shown on the board, so you have to pause the video and take some notes because we're not going to go over every detail. Here's the graph, this red graph of the original function. The green dashed line is the graph of the first derivative, and the blue dashed lines are the graphs of the second derivative. If we want to actually find the first derivative, we have to use the product rule. So it's the first function times the derivative of the second, plus the second times the derivative of the first, which we can rewrite this way. Normally, if we were just finding where the first derivative equals 0, I would just set this equal to 0 right here. But since we're going to also find the second derivative, it's probably a good idea to get a common denominator and combine this into one fraction. So we'll get a common denominator of 3 x to the 2/3 times x plus 3 to the 1/3, and that simplifies to x plus 1 over that common denominator. The 3's actually canceled out. So there's your first derivative right there. And that tells you that the critical numbers are when the derivative equals 0, which happens when the numerator equals 0, which happens when x equals -1, or when the derivative is undefined. Well, it's undefined when x is 0 because you can't divide by 0. It's also undefined when x equals -3. Same thing, we'll get a 0 in the denominator. So there's the critical numbers on the number line. -3, put an x to represent that, -1 and 0, and x there to represent the fact that the derivative is not defined there. And we'll apply the first derivative test to find values in each interval created by those critical numbers. So test number to the left of -3 might be a -4. What's f prime of -4? Well, just picture putting a -4 in for x here. That numerator gives you a -3. If I put a -4 in for x to the 2/3, I'll take the cube root of -4, which I can do, but then I'll square it. So that's positive. But over here, -4 plus 3 is -1. The cube root of -1 is negative. I think you get the idea for the rest of these. So derivative positive, function increasing, derivative negative, function decreasing. That means there's some kind of local maximum at -3. And if you put -3 into the original function, you'll see you get a 0. And there's a relative minimum here. But there isn't one at 0, 0 because the function doesn't change from increasing to decreasing. I'll make note of the fact that this is what's called a vertical cusp here. If you look at f prime of something just to the left of -3, you get a positive number. And if you put more zeros in here, it got closer and closer to -3, this number would just continue to grow. And to the right of -3, it would look like this. So this is what's called a vertical cusp. At 0, there's actually a vertical tangent line because the slopes from both sides of 0 are approaching positive infinity. Okay, that wasn't asked, but I just thought I'd mention that. And so here's f prime. How do we find f double prime? Well, we got to apply the quotient rule. What a mess. Denominator times the derivative of the numerator. I could have shown a 1 here for the derivative of the numerator, minus the numerator times the derivative of the denominator. Here, I'll mention that I put these fractions so that the exponents were positive, and then I realized I got a complex fraction here. If I multiply numerator and denominator of the big fraction by the LCD of all of these two denominators right here, I will clear the equation of fractions. So if I take this 3x to the 1, this LCD times this first term, all the fractional exponents disappear. And the same here, when I take this LCD times the contents of what's in the brackets here, I get x plus 2 times the quantity x plus 3, and which all simplifies to, well, guess what? It simplifies to, I could put this negative out in front of the 2. Negative 2 over x to the 5/3, x plus 4 to the 4/3. This never equals 0, but it's undefined at 0 and negative 3, so we can test in each interval. It looks like the concavity changes at 0 from up to down, and that's what the graph actually looks like. It looks like from, we were concave up here, but then at 0, 0, went to concave down. There you go. Hope that helped. If you have any questions, post a comment.